Now that we've talked about line integrals in general of regular real valued functions, let's see how vector fields figure into all this. So a vector field is a function that takes either 2 or 3 variables, whether you're talking about a 2D or a 3D vector field. But the main thing is it gives you a vector instead of just a single number. It gives you a vector. We can break up the components of these vectors, call them P and Q, or in the 3D case, P, Q, and R. Each of the P, Q, and R are regular real-valued functions, and the vector field packages them together as a vector. So let's look at the 2D version. Let's look at the P and Q version right here. And so we're working in the plane, and let's say we have a curve with a starting point and an end point called C. All right, so what kind of line integral can we compute? We can do the following. We can integrate over C the following: f of xy dot, and that is a dot product, dr. So let me try to explain what's going on here. Instead of ds or dx or dy, we have dr, and it's a vector differential piece. This is new. What in the world could this mean? Well, let me try to explain. If we take our C, and as we often do, we break it up into little pieces. Okay. Now recall that when I say R is the parametrization of the curve. Right? R is the function that actually traces out this curve. If you remember from multivariable calculus, what this vector actually is a vector from the origin to the curve. So, you know, when t equals 0, it's here. When t equals 1, maybe it's there. When t equals 2, it's here. And as t goes up and up, it traces this out. The tips of the r vectors trace out the curve. So if I look at two r's that are right next to each other, like, in fact, let me get rid of all those now. Let me just look at two of them, maybe this one and then this one. So that's one r, and then a little bit later that's another r. So what's the dr, or delta r? What's the change in r? The change in r would be right there. So it would be, I mean, it's the first, let me say it's the second one minus the first one, right? A d or a delta is the change, the change in two r's. And if you remember your vector arithmetic rules, subtracting two vectors, it's the head-to-head rule. So we want the dr then would be the vector that goes from the head of r1 to the head of r2. But you see what we get is a little vector that is sort of like along the curve. So dr is along the curve. It's tangent to the curve. Its magnitude is the arc length. So in a way, we're still weighting by arc length, but it's more than just that number. It's also a vector weighting, and the direction is in the direction the curve is going. So there's two things going on here. Again, it's the arc length is the magnitude of this dr weight, but it's also the direction, which is tangent to or along the curve. So that's what we're doing. That's what the dr is. It's a vector version of ds, if you will. All right. Now, this dot product, let's talk about that. So we recall that f, right, is a vector field, so it's placing a vector at every point in the plane, but we don't care about the points that aren't on the curve. We just care about the points that are on the curve. So at every one of these points, there's whatever f is doing, etc., etc. Okay, so right at this point, maybe f is going this way. All right, so we have f at this point, the beginning of this little sub piece of the curve here, going off in this direction. You know, whatever f does, f doesn't have f is not connected to the curve, so f does whatever it does. But then we have the curve and our little dr piece going this way along the curve. So what we're doing here is we're doing the dot product, and what that means is it's the part of f that's going in that direction. It's like we're breaking up f into a part that's going with dr, and then the part that's like just totally perpendicular to dr, and we're only taking the part that's with dr. So it's like we're only counting the part of the vector field that is sort of lined up with the curve. Hope that makes sense. Yeah, in fact, if f were totally perpendicular to the curve, that would be like, it would be like 0 at that point. We wouldn't be counting any of that in our integral. All right, so there's this extra layer of stuff going on because of the vector, but again, we are still weighting by arc length, but the dot product with the dr means we're only counting the f part that is like going with the curve in the direction that the curve is going. Okay, so that's like the pictorial or the geometric intuition about what in the world this line integral of a vector field is and what it's counting. It's like adding up the vector field, but only weighted by arc length, but only the part that's pointing in the direction of the curve at that point, if that makes sense. Okay. Now, how do you actually compute it? Well, in practice, the way that generally works is the following. We actually do this dot product. Let's think about this. So if f, remember, is p I plus qj, and I'm just doing a two-dimensional one, but it would be plus rk if I were doing a 3D one. Now dr, if you think about it, and if you just go back to this picture of what dr was, it was this little green guy that's now covered up. It turns out it's not too hard to believe or to think about. The components of dr are just a dx and a dy. I mean, actually, I can draw it. Here's the dr. So yeah, I mean, if you just make a right triangle out of it, dx, dy, you can see that those are the horizontal and vertical components. I'm not doing a Pythagorean theorem thing because I don't want it. I don't want the magnitude of it. I just want it as a vector. So just dx is the horizontal component and dy is the vertical component. So then if you remember the dot product just means you multiply the corresponding components and add them together. I get p dx, the p goes with the dx, and the q goes with the dy. So I get that, which really is two line integrals. One is a dx line integral, and the other is a dy line integral. And you just add them together. Now remember, let me just say that the answer is a number. Your final answer should just be a number. This is a number, and this is a number, and then you add them together and you get a number. The answer to this is not a vector. And that makes sense because we are doing a dot product, and remember the dot product of two vectors is a number. The fact that we're integrating doesn't change that. It's still just going to be a numerical, a scalar, a single number answer at the end. So even though we're working with vectors to start, the answer is not a vector. Okay. And you just have to do these two separate integrals. One is a dx integral, the other is a dy integral. You do each of these line integrals the way we did before. You don't do either of them ds. You don't do either of them with respect to arc length. So that's interesting. And here is actually the reason why we even talk about dx and dy line integrals. If it wasn't for this application right here, we would only do ds line integrals. But here's where it comes up. So this is how it works. Refer to your textbook for some good examples of how to work this out. Remember that you can do it in 3D as well.